it's time to start. Good morning, everyone. There's nothing special to announce except for the ones that I've already talked about yesterday. No office hour after the lecture today, and PA6 and quiz 22, 23, and 24 will be doing this Saturday. And so you know that today there'll be just two quizzes, 23 and 24. And the topics today will be these. Okay, so yesterday we overviewed TCP. So TCP does a lot more than just reliable data transfer. So today we'll be spending some time to tell more about TCP sending packets with the sequence number counting bytes a little bit more, as well as TCP is sending data both directions, as opposed when we were talking about all those RDT finite state machines. We kind of assume data only go one way and then act the other way. So we always have a sender side of finite state machine and the receiver side of finite state machine. In TCP, you can think of this way. There'll be a pair of sending, receiving finite state machine from client to server, and another pair of sending, receiving for the server to client. All right, so these will be the first set of videos, TCP, counting bytes and sending data by directions.
TCP sequence number and ACK numbers, these are very important fields. Let me elaborate more here. First, the sequence numbers. So what the sequence number says in the packet header is to tell you this: the byte stream number of the first byte among all the data bytes in the packet. So, but what is the byte stream number? Yeah. Let me explain. This is the original message, which can be really large, generated by the application layer process. Now, as it's pretty long, right, each byte can be indicated in sequence in byte stream number. So this is byte 0, byte 1, byte 2, byte 3, byte 4, and so on and so forth. So these numbers, these serial numbers, are the byte stream numbers. So when such a message arrives at the transport layer, the TCP sender is going to what? Break them down into smaller parts. Let's assume that in the first segment, it contains only 3 bytes of the data. So in the header here, the sequence number is going to be what? The byte stream number of the first byte of data, which is 0. For the second packet, in the header sequence number field, what should be the value? It should be the byte stream order of the first byte of all the data, right? So see here. Okay, so that's what sequence number meant. And it tells you where the first byte of this data packet is in the original message. So we could track whether all the bytes in the original messages are being transmitted successfully. Second, the acknowledgement number. Now to explain this, let me tell you, TCP implements, just like go back in, cumulative acts. So that number there, based on your knowledge of go back in, should indicate what? The last byte of all the data received correctly at the receiver and in sequence. But, well, it's actually not quite. So TCP's acknowledgement number is actually counting 1 byte further. So it's the next byte the receiver is expecting. So that number is the number of the next byte the receiver is expecting. Therefore, it will also be the what? The sequence number of the next data packet coming from the sender. And with that said, many of you will probably guess that TCP's reliable data transfer mechanism is similar to go back in. You are actually correct. So let me borrow the diagram that I've been using to explain the sender side of the behavior of go back in here. The only difference is just that previously, now each rectangle indicates a packet, but now we are counting bytes instead of packets. So each of these are what? Bytes. So we have green bytes, yellow bytes, blue bytes, and gray bytes. But similarly to go back in, the green bytes are what? The bytes that are already sent and acknowledged. Yellow ones are the bytes sent and not yet acknowledged. Blue bytes are those usable, so if there are more data the application layer process wants to send, we could now turn these blue ones to yellow. So usable but not used. gray ones, not usable because it's what? Outside of the window size, outside of the window limit. Now, sender generates a data packet. What's going to be in the sequence number is what? The first byte of the data and the byte stream number of it. And if an acknowledgement is coming back to the sender, acknowledging this packet, the acknowledgement number here is going to indicate what? The byte stream order of the next yellow packet. So this first one here is going to turn green. Yeah, so add number here is the first yellow next. And the last bit here is again about TCP's RDT being very similar to go backend. So if you recall, go backend's receiver, when it receives out of order packets, what does it do? It drops all the out of order packets. Now that is actually a wasteful use of network bandwidth, isn't it? So TCP here allows a bit more flexibility. The programmers themselves can decide whether to buffer the out of order packets or to drop them.
All right, so that was what byte count meant. Okay. Good morning, Amelia, and Yo Yu is very curious if there's anyone alive there. Okay, so yeah, some of you are, I hope. Next, as usual, let's take a look at an example so that you get the idea of byte count a little bit more clear. And from that video earlier and also the overview video, you probably can guess now that TCP's RDT is more pipelined and go back in, right? It is very much like go back in. But let's check out an example counting bytes, okay? And knowing what is the sequence number and ACK number for each of these packets we'll be sending back and forth between client and server. So here's the video for the example.
Now let's exercise what we learned about the TCP sequence numbers and ACK numbers using a simple telnet scenario. The setting is this. We are here at host A. We've already started the terminal and it's connected to the remote machine, host B. So what happened in the telnet is this. When we hit C, a key locally, okay, so user type C, what happened is this. Host A sends a byte, that character C, to the remote machine. Now the remote machine is going to receive this and see what to do with it. Okay. Now because it's a very straightforward character C, not like escape or control C, therefore what it does is going to be simply echo back the character C to the local host. So host A here will receive the echo C and then display on the local terminal. So once again, host A here has 1 byte to send. Host B here has 1 byte to send. And that's the scenario. Now, 1 byte of data generated by the telnet process. As soon as it arrives at the transport layer, we're going to add header to it. So sequence number, ACK number being added to it. And the data is simply a character C. Now, when this packet arrives at host B is going to what? Yeah, echo with the same character C.